In this problem, we'll be calculating the net electric force acting on one charge, in this case Q3. It has two forces on it, one from Q2 and one from Q1. So we'll draw those forces. The force due to Q2 on Q3, which I'll call F23, points towards Q2 because they're of opposite sign. The force due to Q1 on Q3, which I'll call F13, points away from Q1 because they are of the same sign. So to find the magnitudes of these forces, we'll use Coulomb's law. So I'll do F13 first, which is K magnitude of Q1, magnitude of Q2, over the distance between them squared. Okay, putting in values, we have Coulomb's constant, 9 times 10 to the 9 Newton meters squared per Coulomb squared. Q1 is equal to 5 microcoulombs, so it's 5 times 10 to the minus 6. And Q3 is also 5 microcoulombs, minus 6. And root 2 squared is 2. A is 0.1 meters squared. Putting those values in, we get for F13 11.3 newtons. Okay, now we repeat that process for F23. And once again, using the magnitudes of the charges, you do not put negative values into Coulomb's law. It's just a magnitude equation. And the distance between 2 and 3 is A. So once again, we have 9 times 10 to the 9. Q2 in this case is 2 microcoulombs. And Q3 is 5 microcoulombs. And the distance between 2 and 3 is just A squared. Whoop, forgot squared. A squared is 0.1 squared. And that just exactly equals 9 newtons. Okay, those are the magnitudes, but in order to get the vector resultant of those two forces, we have to go to components. So we'll make a table of components. And for each force, we'll calculate the components. So for F13, it has an x and a y component. The x component will be 11.3 cos 45. And that 45 degrees comes from the fact that this vector is 45 degrees above the x-axis. So the x component is cos 45, which is equal to 8 newtons. And the y component is sine 45, which is also equal to 8 newtons. And both those components are positive because they're in the first quadrant. Now for F23, it has an x component in the negative direction, negative 9, but it doesn't have a y component, so that's 0. So the vector sum of these two forces, F net, is equal to negative 9 plus 8, which is negative 1, and 8 plus 0, which is 8. Now we can write this net force in I hat, j hat notation as negative 1 I hat plus 8 j hat newtons. Or if you want the magnitude and direction, you can apply the Pythagorean to those components. So we have 1 squared plus 8 squared, square rooted, comes out to 8.1. And the angle, inverse tan of y over x, works out to 82.9 degrees. But we have to be careful about the quadrant that that force lies in. It's in the second quadrant because it has an x component. And that angle I've just calculated is this angle with the negative x-axis. So to be really correct about writing that vector in terms of its magnitude and direction, you'd need to use this angle, 180 minus 82.9, which is equal to 97.1 degrees. And so we would write F net as 8.1 newtons at 97.1 degrees. And that's the final